Let's remember where we've been. We have a one-dimensional discrete dynamics. We have a limit cycle that we're trying to establish, and you'll remember the limit cycle is an isolated attracting periodic orbit. And so we'd like to understand how to show that this orbit, I'm not doing a very good job of outlining it, but this orbit is actually attracting, that is, initial conditions have orbits that converge down to that cyclic periodic orbit. Okay, so we want to establish this isolated periodic orbit as an attractor, and that means that we need to show that any initial condition that starts close by is going to have an orbit that gets closer and closer and closer and closer and closer. Forgive my drawing. I didn't draw that very well, but I think you get the idea that we're trying to get closer and closer and closer, whether we started inside and then spiral out, or we started outside and then spiral in. We need to be able to show that that's what's happening. The ingredients of this analysis are not that complicated. They look a lot like the stability analysis we've done in other units. We have a section. You recall what a section is. In this case, it's the place where the guard function for the compression mode goes to 0. What's that guard function? That guard function says when chi dot goes to 0, that is when the descent instance of the mass through the spring reaches its bottom, and we start decompressing again. That's the point at which we're going to say that the compression mode has ended. And so we're looking for the set of initial conditions, chi and chi dot, that make the compression guard function gamma comp vanish. And the mathematicians have a notation for this notion of inverse image. This notion is all those those chi and chi dot pairs in the plane that make gamma comp vanish is called the inverse image of 0 under this gamma comp map. And it's a little bit confusing because gamma can't itself be invertible. It's not that gamma is invertible. Gamma is going from 2 space to 1 space, so it couldn't possibly be invertible. But remember, the mathematicians overload their notation often, and here what they're doing is they're showing you that the inverse of the set 0, the set of initial conditions that go to 0, is exactly the set chi dot equals 0, and I've painted it in this orange color on the figure. So here's this section that is the set of chi and chi dot pairs that send the guard function gamma comp to 0, right? And that's the section that we're choosing. Notice that we have two variables, chi and chi dot. This x variable is a two-dimensional variable, so it's got components chi and chi dot. And we've got one equation in two unknowns. We've got one equation which is going to 0. We're specifying the 0 set of one equation. And therefore, we know we're going to have just from the two variables, we're going to get a one-dimensional set of initial conditions. And that's, again, that's what this section is represented. Section just means that all initial conditions nearby flow through. That's what it means to be a section, if you recall from that definition. Okay, so we have a section, and what we're going to do on this section is we're going to look at the map called the Poincare map or the return map that takes the bottom at a given instant and expresses the composition of flows through to the next bottom and expresses the next bottom as a function of the previous bottom. And that's called the Poincare map, or the return map. And that's the thing that we're going to be analyzing. The discrete dynamics of that object is what we're going to be analyzing. Let's drill down on what the meaning of this Poincare or return map might be. What is it? Why is it helpful? What is it going to tell us? Okay? It's a function that specifies how the next crossing, let's say to here, depends upon the value at the previous crossing. So it's a map that takes initial conditions on this section into the next return conditions on that same section. And it's going to characterize the cyclic behavior. Since the value along any section equivalently expresses the qualitative properties, the asymptotic stability of this periodic orbit is equivalent to the steady state convergence of the return map to a point along this section. And that's what we're going to be focusing on in the analysis that we're about to do. As always, the choice of section, the choice of coordinates, is up to the user, it's up to the analyst. And we're starting with these physically meaningful end of compression phase or bottom coordinates, that is the set of extensions, spring extensions down where the spring mass travel is changing its direction. But we didn't have to use these sections. Any transverse curve, doesn't even have to be a straight line, any transverse curve will do. For example, we could instead have taken the section to be the liftoff condition, which is the set of points that make the decompression guard function go to 0. And remember, in these coordinates, in chi coordinates, when chi goes to 0, it says that we're exactly lifting off because the spring has suddenly become relaxed, okay? And so in this section, we're painting the inverse image of the chi and chi dot points that make the guard function for the decompression mode vanish. We could have used those liftoff coordinates instead. Alternatively, and as we're going to find convenient in this analysis, we could instead be looking at the end thrust conditions. Namely, we could go to the end compression and we could use the reset map from analysis, and we could introduce this section. Notice that this section doesn't appear to be quite as neat because it doesn't look quite as orthogonal to the flow, but it works perfectly well. I think you can see that all the flow lines are piercing through, so it's a perfectly good section. And so we're using the reset map from bottom to end thrust coordinates, which is going to take the chi dot or the polar coordinates at bottom into the end thrust polar coordinates, and that's going to turn out to be the one which is most useful to us. Crucially, all of these one-dimensional representations of the Poincare or the return map are just changes of coordinates away from each other, and so they can't be giving any different analysis. Each of the stability analysis in whatever coordinate system we do is going to give us exactly the same behavior, because I think you can see that if you're converging down, if you're getting closer and closer and closer each time so that your points are converging down to the fixed point, as we'll call it on this line. It doesn't matter whether you do it on this section, that section, or any of these other sections. So all one-dimensional representations of the energy in the cycle at a given instant are going to give us the same result. Let's see how to do this. The bottom coordinates can be thought of as spring energy, right? Because there's no kinetic energy left, and so the only thing that we've got, the meaning of this chi extension is the energy that we're going to call rho at bottom. How much potential energy is there in this spring? That's how much energy there is in the hop at this instant. The total energy at maximum compression measures the spring potential, and it's a complete characterization of the state. The Poincare map is going to look at the spring potential energy at the next compression, at the next maximum compression, as a function, Poincare map, RVH, of that same energetic component in the previous hop. That's what we're going to study. Okay? And it's expressing the next bottom energy as a function of the previous bottom energy. Now, if you do the mathematical analyses and the models that we've introduced already, you're going to end up getting this rather complicated map that we've introduced before. So this Poincare map of the Rayburn vertical hopper as in the bottom energy coordinates is the product of an exponential map times a square root map. And when you plot it, it looks like this. Now, I'm plotting together with this blue Poincare map, I'm plotting the identity map. The identity map is the thing that takes any variable, in this case the energy at the bottom, and just returns the same energy. And what we're going to understand is that the fixed points, which are all important to us, which characterize exactly the cyclic component of this orbit, we're returning again and again and again to the same bottom point. The fixed points correspond exactly to the crossings of the return map in blue with this identity map in orange. And the way to think about this is to imagine starting with some initial bottom energy. Let's say we started with rho 0 here. And let's plot rho 0 on a new axis down here, the abscissa of this plot over here. And then let's flow forward. Let's flow forward with this map and see where the flow takes us. If we look at what this map does to rho 0, we can see that P, the return map at rho 0, is some new value of energy, rho 1, and that is the next energy that the hopper experiences in consequence of its having bounced up through the air and then compressed back down to its next bottom. So what we want to do is we want to now understand that rho 1, the next energy, becomes the previous energy for the next hop. So how are we going to find where rho 1 is on the abscissa? Well, we do what's called the spider web diagram, namely, we say, oh, I can understand where rho 1 is by realizing that if I take rho 1 on the ordinate and I project it back down to the abscissa through this identity map. Remember, this identity map is saying anything that fits this square box has the same value. So if rho 1 was up here on the ordinate, then rho 1 has to be down here on the abscissa, okay? So now I know where rho 1 is, and what I can do is I can apply the blue function, the Poincare return map, to rho 1. Let's see what happens when I apply to rho 1. I'm going to get somewhere up here, and there I am. Okay, so rho 1 gets evaluated to be rho 2, so that the second hop, so we started with rho 1, we got to one new next energy, rho 1, then we started at rho 1 again, we applied the return map, that is we bounced through the air and then back down into compression, and we got rho 2, okay? So where's rho 2? Well, rho 2 shows up at this height. I'm going to do the same thing. I'm going to figure out where rho 2 is on the abscissa. I'm going to apply the return map again to rho 2, and on and on and on and on. So I hope you can see that I'm getting an expression. So from rho 0, we went to rho 1, and from rho 1 we went to rho 2, and from rho 2 we went to rho 3, and on and on and on. So that's what this Poincare map is expressing for us. The Poincare map is expressing the way in which the next bottom is a function of the previous bottom.